Alright, so in this video we're continuing with limits, and today we're actually going to be sort of finding a limit of this function that we have here on the right. So this function, as you might know, is the function of y equals x squared. So what we're actually going to do, y equals x squared, what we're actually going to do is we are going to find the slope of the tangent, because remember, when we're doing limits, really all we're asking ourselves is what is the slope of a tangent line of a curve. Because again, it's difficult to get the slope of a curve because, well, by definition it's curved, and for a line it's not a curve, it's a line, again, by definition. And so how are you supposed to find a slope to a curved line? So we're going to find the slope of the tangent line, okay, of the tangent line to this function y equals x squared, to y equals x squared at a specific point, and that point is going to be the point 1, 1. Okay, so before we even kind of get going, let's just graph what we have here. We have our y equals x squared graph. We'll put little arrows on the end as well. And we have this point 1, 1. So we'll put that point right here, 1, comma 1, and we'll call this point P, just because we can. And that's the point 1, comma 1. And so now what this question is asking us is to find the slope of the tangent line at this point. Now, of course, we can try and approximate the tangent line and what it is. And, you know, if you kind of eyeball it, you can see that, oh, maybe it looks like this. Oh, I don't know, maybe it looks like this. I don't know, maybe it looks like this. You can try and approximate it, but you're never going to be able to get an exact answer. And what we want in math is an exact answer. So we need to mathematically somehow go through the process of, okay, how are we going to be able to find this point? And so the answer to that is we're actually going to take another point, and you'll recall this from the introduction to limits video. You're gonna take another point, some random point. Let's just put it. I don't want to put it here because again, I want to emphasize this is just a random point, and let's say it's right here. And we're going to call this point, it's going to be a point on our curve, and it's going to be point Q. And I'm going to ask myself, okay, what are the coordinates of this point? Now, again, I don't want the specific coordinates like the x and the y coordinates. I want in general. If I were to move this point somewhere else, what would be the coordinates of that point? Well, the x coordinate would just be x, right? And the y coordinate would just be y. But I want to keep everything with the same variable. I don't want to use x's and y's. I want to use just x's or just y's. In this case, I want to use just x's. So instead of typing in, instead of writing in here y, what does y represent? Well, looking at the equation here, y represents x squared. So instead of writing y, I'm going to write x squared. Means the exact same thing, except now it's just in one variable, that variable being x, instead of two variables, x and y. Okay, so we have a point P, we know the coordinates of it, we have a point Q, we have how to find the coordinates of the point Q, but we don't know what that point exactly is. And the question that we're going to ask ourselves now is, as our point Q approaches, okay, this is a little arrow, approaches P or gets really close to P, okay, we're going to say as Q approaches P, our approximation to the tangent line, gets better. Okay, so let's see, I mean, I wrote this down. Is this true? Well, let's think about it. Again, if you recall from last video, you'll know that it's true, but if we take this point P and this point Q and we connect it with a line, we actually get a secant line. Okay, we get the secant line QP. Okay, and what we discussed in the previous video is as Q gets really close to P, the approximation of the secant line gets really good, And therefore, it gets so good that we can actually say that the approximation of the secant line is the exact same, that is, it is equal to the tangent line at the point P. Okay, so we figured that out in the last video, and so we're just kind of restating that here. So we're saying as Q gets really close to P, our approximation to the tangent line gets better. Mathematically, what does that mean? Well, that means, like I said, as Q gets closer to P, the slope of our secant line gets really close to the slope of our tangent line. And in fact, what we'll see by the end of this video is that the slope of the secant line is actually equal to the slope of the tangent line. But for right now, we don't know that, so we're just going to say that they're approaching one another. Okay, so that's kind of the idea that we have. Okay, and that's what we're going to build off of. So now that we have that basic idea, what we're going to do is we are going to try and solve this. And by solve this, we're going to try and get Q to be as close to P as possible. And therefore, we're going to get our slope, our secant slope, to equal our tangent slope, which at the end of the day is what the question is asking us. Okay, so let's kind of go over what is slope. Well, if you remember all the way back to when you started learning about linear equations, you had an equation for slope, and that equation was slope is equal to rise over run. Some of you may remember that. And what exactly is rise over run? Well, rise over run is just the change in y over the change in x. And again, what does that mean? Well, that just means y2 minus y1 over x2 minus x1. This should just be review from like grade 9. Okay? So we know that. And now the final question is, okay, well, what is y2, y1, x2, and x1? Well, if we're specifically talking about the slope of our secant line, then what we can do is we can go back up here and see what y2 and y1 actually is. Okay, so y2 is actually x squared. Okay, so x squared minus y1, which is just the value of 1, divided by x2, which is just x, minus the value of x1, which is just 1. So if we're talking specifically about our secant line, our rise over run is going to be x2 minus 1 over x minus 1. Okay? And again, remember, the end goal here, we're asking ourselves is what happens as this x value gets really, or sorry, this point Q gets really close to point P. Okay? So we want our point Q to basically equal our point P, but if we try and make point Q equal point P, we run into two problems. One of them being that then we have the same point. And if we have the same point, well, we know that we can't make a straight line with just one point. We actually need 2 points to connect those 2 points, and when those 2 points are connected, you have your line. Okay, so we can't actually let Q equal P. That's kind of the first problem. And the other problem kind of stemming from that, or that you might be able to see from that, is what if let's say we did let Q equal P. Okay, what if we say, you know, screw the rules of math, we're going to let Q equal P. Well, if we let Q equal P, we're going to have point P, which is 1, 1, and point Q, which is also 1, 1. And if we try and sub that into our equation here to find the slope of the secant line, we're going to get 1 squared minus 1, which is 0, divided by 1 minus 1, which is 0. We're going to get 0 over 0. And we know that 0 over 0 is mathematically not defined. Okay, it's undefined. And so that's our second problem. Mathematically, even if you wanted to ignore the rules, mathematically you wouldn't be able to do it. And so this is why we need the idea of a limit. Okay? So really all the idea of a limit is we are going to let the value of x get really close to the value of 1 in this case, because again our point up here P has a value of x equals 1. So we're going to let our x get really close to 1, but we're not going to let it equal 1. Okay? And that's all we're doing with limits. That's literally all we're doing. And for right now, we're going to take a pretty, Stone Age approach as to doing that by literally just brute forcing it and getting that calculation done. But before we do that, I want to simplify this equation a little bit. And the way I'm going to simplify it, again, this isn't necessarily necessary, but I'm going to do it just to show you kind of some of the tricks that we will be using later on to help us with limits. Okay, so I want to simplify this, and what I can do here actually is I can factor the top, and we'll see that we get some cancellation. So if you were to do that, you would get x plus 1 times x minus 1 divided by x minus 1. And what you see here is that the x minus 1 can be crossed out, and you will get x plus 1. Okay? And now a few things that we can do here. First things first is you might be wondering, are we allowed to just cross out these x minus 1s? The reason you might be wondering that is because technically we have a domain issue. Okay, and our domain issue is that x cannot equal 1. Because if it does equal 1, we're going to get a 0 on the denominator, and if we get a 0 on the denominator, we know that that's not allowed in math, that's undefined. The reason that we are allowed to cross out this quote-unquote domain issue is because it's not actually a domain issue. Because by definition, when we do our limits, we are not, again, by definition, and by what it means to do a limit, we are not letting x equal 1. We are letting it get very close to 1. And so you can actually do this cancellation and be left with x plus 1. And the second question you might be asking is, now we have x plus 1, well, we can just substitute in 1 into here, and we're going to get 1 plus 1. 1 plus 1 is just 2. That's allowed. We're allowed to do that. Why can't we just do that? And you'll see later on that you actually will be allowed to do that. Okay, and that is how actually we'll solve a lot of our limits by direct substitution. But for right now, what we're going to do is we're going to kind of do it the brute force method, because maybe you will not know some of these tactics or techniques that you can use to simplify your expressions, and so you might have to, use this old school method, which is literally just plugging in numbers into a calculator. So what do I mean by that? Well, all I mean is, remember, with limits, we're trying to let x get as close to we're trying to let our point Q get as close to our point P. Our point P has a x value of 1, so we're going to let x get as close to 1 as possible. Okay, and the way that, I can write that is I can say, okay, well, what happens is Q, so what happens as Q approaches P, or in other words, what happens as X approaches 1. Okay? So what happens? Well, what happens to our slope, our secant slope? Because remember, as Q approaches P, we're getting closer to that point P, and therefore the slope of our secant is going to approach the slope of our tangent, and eventually it's going to equal the slope of the tangent. So that's why we want to ask this question. So as Q gets closer to P, or X gets closer to 1, what we can actually do is we can just make a table, right? We have our X value of X equals 1 here. Okay. And on the left and on the right, we're going to have something like, let's say, we'll have a few different examples here, I suppose. Like this, we'll have 3 numbers on the right and 3 numbers on the left. And let's say we start at here on the right, and we're going to start at x equals 2. And then we're going to go to x equals, let's say, 1.5. And then when we get really close to 1, let's say x is equal to 1.001. Okay, and same thing from the left-hand side. So we can start off at, let's say, x equals 0. We'll keep it even on the left and on the right here. X equals 0.5, and x equals 0.009. Okay, so what is happening to our slope as x is approaching the value of 1? And notice that we're going from both the left-hand side here and the right-hand side. Okay, and again, we don't care what happens at x equals 1. Okay, we care what happens as we get very, very, very close to 1 from both the left-hand side and the right-hand side. Well, if we take a look at it, what is our equation for the slope of the secant line? Okay, so m secant, slope of secant line. the equation of that is x plus 1. We calculated that up here. Okay, and so now we can just substitute in our x value. When x is equal to 0, we get 0 plus 1, which is 1. It's equal to 0.5, we get 1.5. It's equal to 0.009, we get 1 plus 0.009, so 1.009. Okay, and we can continue this with, sorry, that shouldn't be 1.009. That should be 1 point, or 0.99. There we go. And then we'll get 0 point, or 1.999. And on the right-hand side here, we can do the same thing. Substitute in our x value. We're going to get 2 plus 1, which is 3. We're going to get 1.5 plus 1, which is 2.5. And then we're going to get 1.001 plus 1, which is 2.001. And you can imagine that we can get even more and more and more fine here by doing 0.99999999999 and 1.00000000001. And remember, with limits, what we're saying is that we're getting infinitesimally close. We're getting so close we're having an infinite amount of zeros and then a 1 at the end, or an infinite amount of 9s. And we're asking ourselves what happens when that happens, right? So in this case, what we can see is from the left-hand side, as we are approaching 1, well, we can see our value going from 1 to 1.5 to 1.999. If you do a few more of these, you'll basically start to see that we're getting close to the value of 0. We are, 2. We are approaching 2. And if we go from the right-hand side, again, you can see here 3, 2.5, 2.001. If we kept going, you'll notice that we are approaching the value of 2. And so what we can say is that as q approaches p, or as x approaches 1, the value of the slope of our secant approaches 2, because from the left-hand side, we're getting to the number 2, and from the right-hand side, we're getting to the number of 2. Therefore, in the middle, it must be the number 2, right? Okay, and it's important that these two numbers match. If they don't match, then there's some issues, and we'll talk about that in a later video. But for right now, they match. Great. So we can say, what we can actually say, because of limits, is we can say as x approaches 1, the slope of our secant approaches 2. And, okay, so we've said that, right? One more thing that we can say about this is kind of the leap here. Since x is approaching 1 and the slope of our secant is approaching 2, what we can say here, and this is the big step, the slope of our tangent is equal to 2. This is kind of the big thing. We have now found the slope of our tangent, and we've said that it is equivalent to the slope of our secant because of limits. We're allowed to say this, okay? So this is the big step. This inference that the slope of the secant is approaching 2, therefore the slope of the tangent is 2, is what makes limits so beautiful and so amazing to work with. Because now we have found the slope, okay, we found the slope of the tangent line to this graph up here, okay? We found the slope to this tangent line up here at the point x equals 1, or at the point p 1 comma 1. And so what we can say now is we can say that the slope of the tangent is equal to 2, okay, which is what the question was asking us. And if we really wanted to, we could also find the equation of the tangent by just plugging it into our point slope form. So remember, that's y minus y1 equals m times x minus x1, and this is just y minus 1 equals, now we have a slope, which is 2 times x minus 1, and if you simplify this, you're just going to get y equals 2x minus 1. 2x minus 1 is the equation of the tangent line at the point x equals 2. You may be wondering, well, what does that look like? I actually have a picture here, which is being overlaid by everything, but let's just scroll down and we'll see what this looks like. So what you see here is uh, actually our original graph of y equals x squared, right? That's the red one. And this blue line is the equation y equals 2x minus 1. And what you'll see right here is exactly the point 1 comma 1. This is the only point where the blue line touches the graph of y equals x squared. Okay, it's the only point where it touches that graph, and therefore by definition it is the tangent line at that point, 1 comma 1. Remember, this is our point P, 1 comma 1. Okay, and what we've done is we've taken our point Q, which remember before was just some random point, and we called it x comma x2, and what we've done is we've walked it over, right? We've just brought it closer and closer and closer until we brought it so close that it was indistinguishable from the point P. Okay, we never let it equal the point P, but we brought it so close to the point P that it was indistinguishable, and because of that we were able to get the slope of our tangent. Once we have the slope of our tangent, finding the actual equation of a straight line is pretty easy. And so that's how we got this blue line. And so you can see here visually what it looks like to find the not only the slope of the tangent but the equation of the tangent line, and how amazing that is when we look at this curve, right? This is a curve y equals x squared, but we're able to get what it actually looks like, right? This is the slope at the point 1 comma 1. And now that we have an equation for the tangent, we can actually do that at any point. We can find the equation of the tangent line at any point on the curve y equals x squared. Okay, so that is what we did in this video, and in the next video we are going to go over different kinds of limits. Okay, different kinds of limits. We are going to also write down what specifically a limit is. Okay, and then we're actually going to find some limits in a very elementary fashion. So that's coming up in the next video.